Welcome viewers to the fifth lecture of online series of lectures of the course of Introduction to Category Theory. Last lecture was about the concept of an OLOG and its key features called types, aspects, and facts. We also saw how we can think of an OLOG as an abstract category. This lecture and in the one following this one, we will discuss some very important category theoretic concepts in the framework of the category of set. Okay? Alright, let me give you a table first. A table where on the left side of the table we have four things written down. 1, product. 2, pullback. 3, limit. And 4, equalizer. On the right side of the table we have co-product. 2, we have push out. On number 3 we have co-limit. At number 4 we have co-equalizer. So the concepts presented on the right are dual to the concept presented on the left in a certain sense that we'll explore later in the lecture. So let's get started with the concept of product. Okay. So what is the product? Product. So let us start with two sets. Let X and Y be sets. Y be sets. The product of X and Y, the product of X and Y, denoted by X brought Y, is defined as the set of all ordered pairs, as the set of ordered pairs X comma Y, where X is in X and Y is in Y. Okay? So theoretically we write it as X product Y is equal to the set of ordered pairs like X comma Y, such that small x is in big X and small y is in big Y. The set of all pairs where the first entry comes from the set X and the second entry comes from the set Y. So there are two natural projection functions. There are two natural projections phi 1 x cross y to x. So how it is projected to x? The entry xy gets projected to the first entry. You see that it's a surjective manner. Okay. So its projection onto the first factor, so we have another projection onto the second factor given by phi 2 from x cross y to y. Element wise, x comma y is projected to the entry 1. This is the projection onto the second factor. Projection onto the second factor. Okay? Good. So we can combine these two projections into a single diagram given as follows. So the diagram is given by x cross y is the product, and we have projection on the first factor x and projection on the second factor y. This is phi 1 and this is phi 2. Okay. Alright, let us take an example of this product of two sets. So we have an example now. Example. Suppose X is a 6-element set 1, 2, 3, 4, 5, 6. Okay? And Y is a 4-element set. The elements are club, diamond, hearts, and spades. Okay. So now, what is this product x cross y in this example? It is a set containing how many elements? There will be 6 times 4, 24 elements in this big set. So, and each of the elements here is an ordered pair, where the first entry of the ordered pair comes from set X, and the second entry of the ordered pair comes from set Y. So, let us list all the elements here. So the first one I'm writing as 1, comma, club. The second one, 2, comma, club. The third one, 3, comma, club. Then we have 4, comma, club. We have 5, comma, club. We need more room. Let us make it a little bigger, the box. And then we have 6, comma, club. The second row is 1, comma, diamonds. then the 2 comma diamond, then 3 comma diamond, then we have 4 comma diamond, then we have 5 comma diamond, and then we have 6 comma diamond. Alright, now we have 1 comma hertz, 2 comma hertz, we have 3 comma hertz, we have 4 comma hertz, then we have 5 comma hertz, and then we have 6 comma hertz. Then we have 1 comma states, we have 2 comma states, we have 3 comma states, we have 4 comma states, we have 5 comma states, and finally we have 6 comma states. So we have 24 elements in this set, as you can count. Alright, so this is X cross Y. Then on the right side we have simply Y, which is just a 4 element set. So the first row corresponds to the club, the second row corresponds to the diamond, the third row corresponds to the heart, and the last row corresponds to the face. And here we have the 6 element set of X, and the elements are the element that corresponds to this column is 1, 2, 3, 4, 5, and 6. So the 2 projections are given by this phi 2 and this phi 1. Okay. So what is this function phi 2? Phi 2 takes all the elements in the first row to club in Y. All the elements, all the order pairs in the second row to the element diamond in Y. All the elements in the third row to the element hearts in Y. And all the elements in the fourth row to the element of spade in Y. Similarly, for this projection phi 1, all the elements contained in the first column are projected to the element 1 in X. All the ordered pairs in the second column of X cross Y, tabulated in here, they are projected to the element 2 of this set X. All the elements here in the third column are projected to 3. All the elements here on the fourth column are projected to 4, and so on. Okay. So I want you to realize that both these projections are surjective but not injective, because each of the elements in the first row is assigned to a single element club in Y. So it's a many-to-one kind of map. So it's a surjective map, but not injective, because it's many-to-one. But it's many-to-one. But well, it's surjective, because all of the elements in this set Y is exhausted. So are the elements in X under the map I1. So they are surjective, but they are not injective. Okay, good. Now you need to do some exercise. So let me write down the exercise number from the textbook. Okay, so do exercise 2.4.1.8 is very important for you to do. Okay. So now I'll describe what it means by universal property of products. Okay. Universal property for products in the category of set products. So by universal property we mean some sort of property which is considered the best. So for products, the universal property is given by the following lemma 1, which states that, so under the name of universal property for product, universal property for product which states that let X and Y be sets for any set, for any arbitrary set, for any set A, and functions these are all also arbitrary functions from A to X. Okay, so we are given two sets, then we choose any set A and functions so that the following are satisfied. And G, a function from A to Y, there exists a unique function. There exists a unique function, from A to X cross Y, which is the product of these two sets, such that the following diagram commutes. Such that we know what it means by commutative diagrams, such that the following diagram commutes. Following diagram commutes. And what is the diagram? So the diagram is as follows. X cross Y is the product, and from it we have an arrow called phi1, which is the projection on the first factor that projects it to this guy to the set X, and on the right we have another projection, the projection on the second factor, and it projects the product onto the set Y. And there is a set A, which is any set A that is written there on the lemma, in the lemma. And from A to X is given a function which is f, and from A to Y is another function which is g. And according to the lemma, there exists a unique function which is given by this dotted arrow. There exists a unique arrow from A to X cross Y. So we have to figure out what this unique arrow means. Okay. So let us do the proofs. So, okay, diagram commutes, and we might write the unique function. So there is a. So I haven't finished the statement of the lemma yet. We might write the unique function. As f cross g, which is a map from A to X cross Y. So this unique arrow that we are looking for is denoted by f cross g, which maps A to x cross y. This is something that we need to find or define, that we are going to define in our proof. Okay? So let us go over the proof immediately. How much time are we left with? 3 more minutes? Okay, I won't be able to finish the proof in 3 minutes. If I don't, then we'll go over to the next segment and do the rest of the proof in the next segment, okay? But let me get started. Proof. Suppose FGR as above, meaning that the way it was defined in, the way it was given in the statement of dilemma, F and G are as above, that is, okay, I explained it here. That is, F is as a map from A to X, and G is another map from A to Y. So, okay, so we are looking for a function from A to X cross Y to provide a function L from A to X cross Y is equivalent to providing a unique element LA, which will belong to this product for each A in the set A. We'll carry on with the next video, next segment, so for now, let's postpone. Thank you.